Hi everyone, Assalamualaikum. Now we move to chapter 1, part 5, and this is about discrete time signals and system. Okay, these are the contents for discrete time signals part. We are going to have a look on why we need these discrete time signals, and then the sampling process, and then we're going to go into details on the discrete time signals in terms of the representation, the type, the arithmetic means the plus minus, multiplication, and also division, and also time reversal as well as time shifting, okay, which involve time transformation. Then we're going to go and have systems, okay, and this is in terms of linearity, time invariant, causality, stability, and memory. All of these type of systems you have learned before in continuous time, but now we are going to apply it in discrete time systems. Discrete time signal is defined only at discrete instance of time, represented as n, and n may assume only integer values. So if you remember, for the continuous time, we represent the signal as t. Okay, for discrete time signal, we represent the signal as x n. Okay, so n we can assume only integer values, and each value in the sequence is called a sample. Okay, after this we will see an example of the values in the sequence. Okay, it means that each of these value here is called a sample. Okay, it is obtained through the sampling process. So since most signals encountered are analog in nature, digitization is required, and it consists of sampling and also quantization. Okay, if you remember, previously I've shown you that if we have a continuous signal, so we can sample the signals at certain time. Okay, so let's say the sampling time here is 1 second. It means that every 1 second we sample the signal at that time. Okay, so we will get the value of the amplitude of that signal. Quantization means that we further divide the signals into several levels, okay, horizontally. Okay, for example, we can say that let's say this is 3 volt, 5 volt, and 1 volt. Okay, we can say that the signals below than 3 volts, we can regarded it as a 0, or more than 3 volt we can say it as 1. Okay, that is another way to digitize the signal, to make the signal from analog to digital. Okay, first we sample, okay, and then we do the quantization, okay, in which the values of this signal at discrete time here is rounded at the nearest integer. Okay, you can put it in terms of 1 0, or you can put also the several levels. For example, if you sample here, okay, you put this one as 5 volt, okay, because it is nearest to 5 volt than 3 volt. Okay, and why we need this discrete time signals? Basically, digital signal processing is more versatile. Okay, any signal processing that involve digital signals, it is more versatile compared to analog signal processing. Okay, and many communication systems also are based on the transmission of discrete time signals for a variety of reasons. It is easier to be processed, easier to be to extract the knowledge or to extract the information when compared to analog signal. And also, sampling a signal allows us to store the signal in discrete memory. Remember the knowledge that you've learned before in digital electronic. Why do we need digital electronic instead of analog electronic? Okay, you can save lots of memory when you sample a signal and you store it in digital way or digital method compared to analog. Because if we compare to the analog, we have lots of values in terms of the amplitude of the signals. And if we use only 0, 1, we can compress the signals and we can put it in the memory with a smaller size. Okay. Also, the outputs of certain sensors that measure physical variables are also discrete time signal. And another reason is complex algorithms for automated controlled physical system require digital computer implementation, and the controlling signals from the computer are also discrete time. Okay, we are living in the world where many things are digitized. Okay, even our TV, digital TV. Okay, and not to mention also our mobile phone and all many technologies right now is also in terms of digital signal. And many consumer products such as CDs, which is already almost obsolete, DVDs, digital cameras, and MP3 also use digital signals. Okay, and recall the classification of signal we have learned before: continuous time versus discrete, in which the continuous time signal takes on values in the continuous interval. On the other hand, discrete time signal only takes samples at certain values of time, okay, according to the sampling time. For example, it takes values every 1 second, so that is discrete signal. We also classify the signal in terms of periodic and aperiodic. Okay, periodic, which is also called harmonic signal, is consistently repeated at certain time period from negative infinity to infinity. The signal is repeated, okay, after certain time. So you can see the pattern is the same after certain time. Based on deterministic and also random. Remember that deterministic signal can be represented with mathematical description. It means that it can be described exactly, for example, at certain time. And if we want to reproduce that signal, it can be done because it is represented or described with exact mathematical description. On the other hand, for random signal, it evolves in time in an unpredictable manner. So we can only represent random signal in terms of variance, means, maximum, minimum, and so on. Okay, now we go to a sampling process. To convert from continuous signal to discrete time, t in the continuous time signal can be represented or is also equal to n multiplied by ts. So this n means the discrete time, okay, in terms of integer, right? In continuous time we say t, but in discrete time we put it as n. And another one is this n must be multiplied by this sampling time, which is ts in terms of second, and this n is also called sample. And the signal representation here for xt here is for analog or continuous, and xn here is for digital and also or discrete signal. Okay, and the process from digital, okay, from analog to digital can be done using the analog to digital converter. And look at this example. This is the continuous signal as input, which is represented as xt. So this xt goes into the analog to digital converter, in which there is a sampling process here. The signals are sampled at equal time period ts, and the signals are converted to binary code. Okay, and the output of the analog to digital converter here is in terms of discrete time signal. So this is an example of discrete time signal values which are sampled at certain time called ts. So we put here as x and ts, and n is an integer. To represent discrete signal, we write in terms of numerical method. Okay, this is how you represent the signal. Xn is equal to, you put the bracket here and put the value of the magnitude of the sample signal. And the arrow here shows the position when n equal to 0. And if no arrow showed here, if there is no arrow here, the first sample holds the position at n equal to 0. It means that if there is no arrow here, the first sample is at n equal to 0. In terms of graphical method, we just plot the signal based on the value represented in the bracket here. So value when n is equal to 0 here is 2. Value when n equal to 1 here is 1. Okay, the next one, when n equal to 2, the value is 3. When n is equal to 3 and 4, the value is 0. When n is equal to 5, the value is 1. Okay, So what happen if, let's say, you have Xn, okay, you have the same number here, 2 1 3 0 0 1, but this, for this example, you have arrow here. Okay, so it means that the number, the signal, when you plot here at n equal to 0, the value of the signal or the amplitude here is 3. So this is your Xn. Okay, and for n equal to 1, the value here is 0. N equal to 2, the value here is 0. N equal to 3, the value here is 1. So this is how to write. And for this, these values, it is at n equal to -1 and also n equal to -2. Okay, this is how you write. So another term which is called discrete signal length. Okay, this is also called size. Okay, it means that this is the number of samples in the signal which you count from the lowest end to the highest end that has a non-zero value. Okay, that's it. Now we look at types of discrete signal. It is actually similar to continuous signal, except for the signal here is discrete, not continuous, just like we've learned before. First, we look at impulse signal. Impulse signal is actually a unit sample function, and it is represented by delta n. For impulse signal in terms of continuous signal, it is represented by delta t, remember? Okay, so for delta n, it is equal to 1 when n equal to 0. So when n equal to 0, the value here is 1. And this is actually the value of the area when n equal to, okay, the area of this line. And then delta n is equal to 0 when it is not 0. So other than 0, other than n equal to 0 here, delta n is no value. And un is equal to 1 when n is bigger or equal to 0. It means that starting from n equal to 0, the value of the amplitude here is 1. And un is equal to 0 when n less than 0. There is no value when n less than 0. So one thing you have to remember is, for discrete signal and unit step function, the value of 1 here, the amplitude 1 here, starts from n equal to 0 to ut, which is unit step function at continuous time, except for discrete signal, it is discrete and sample at ts equal to 1, meaning that every 1 second or every one integer here, it has a sample of values. And for impulse function, it is also expressed as a difference between two step functions. Means that delta n can also be represented as un minus un minus 1. Okay, if you want to perform any arithmetic operation for discrete signal, it's better for you to draw. So first you draw un. Okay, you know that un here, same as this, right? The same as the figure here. So it starts from n equal to 0, 1, 2, up until infinity, and the value here is 1. This is un. Okay, and you want to minus un minus 1. When we see here un minus 1, it means that this is a unit step function which has been shifted by 1. Here, which has been shifted, we draw it here. Okay, when we shifted by 1, it means that it starts from 1 and so on up until infinity. So this is un minus 1. So when you minus 1 by 1 from un minus minus 1 here, you will see that the only left here is, because you have minus this 1, this is 1 minus 1 at n equal to 1. So the only value left here is this, which is also equal to delta n. So this is why we said the impulse function can be expressed as a difference between two step functions like this. we look at arithmetic operations for discrete signal. All arithmetic operations, for example, addition, subtraction, multiplication, and division, are made on each of the sample of similar n. It means that you have to match the n here. For example, here we have x1n and x2n. And x1n has values at n equal to 0, 1, 2. And the value here is 1 to 1. And this is the values for x2n. We look at example 1 here. When x1 plus x2 n, you have to match the values when n is equal. For example, here you add the value when n is equal to 0 at x1 and also x2. So 1 plus 1 here is equal to 2. And then at n equal to 1, you add the values at x1 and also x2. 2 plus 2 here, which is 4. And so on. So this is for first example. For the second example here is actually minor mistake here. This one should be x2. This one should be okay. This one minus this. And then for the first sample at n equal to 0, here is 1, here is 1. So 1 minus 1 is equal to 0. When n equal to 1, this is 2. This is 2. So 2 minus 2 is equal to 0. And then at n equal to 2, this is 0. This is 1. So 0 minus 1 is equal to negative 1. And then finally at n equal to 3, 1 minus, at n equal to 3, 1 minus nothing here. So 1 minus 0 is 1. Divide by x2. So we take the values at the similar n. So n equal to 0, 1 divided by 1 is 1. And then here 2 divided by 2 is 1. And then at n equal to 2, the value of x1 is 1. The value as x2 is 0. So 1 divided by 0 is infinity. So you plot like this. And then here at n equal to 2, there is no value. It means that it is 0. 0 divided by 1, it is 0. So this is simple. x1 multiplied by x2 at n equal to 0, 1 multiplied by 1, which is 1. And then at n equal to 1, 2 multiplied by 2 is 4. And then for another n, the multiplication involves 0. So the answer here is 0. Okay, the next one is time reversal. It's similar to the time continuous signal, in which it has what we call a folding operation, or the mirror image of a signal at n equal to 0. So where yn here is actually x minus, the time here is reversed. If we have xn here with the value of 2, 1, 1, 2, 1 at n equal to negative 1, 0, 1, 2, and 3. So the values of n here will be reversed to another values. Okay, the same value but with different plus or minus here. So for example here, here is negative 1. So the new yn here, which is the time reversal, it will become 1. Okay, and 0 is still 0. 1 here will become negative 1, 2 negative 2, and 2 will become negative 3. And the values of the amplitude here follows the n here. When n equal to negative 1, the new value here is 1. The new value of n is 1. So the value here is 2. Okay. So in other words, that you just reverse the time base here. From here negative 1, it becomes 1. Example, another one is 3 here, it becomes negative 3. And the values of amplitude is still the same. So this is time reversal. Is time shifting. Okay, time shifting, it involves shift the signal to the right or left by ND samples. It is similar to the time continuous signal, except for time continuous, it is represented by T0. Okay, the shifting is represented by T0. For this discrete time signal, it is represented by ND samples. For example, yn equal to x n minus nd, and nd is an integer constant. This is the example of xn. Let's say that nd here is 2. It means that xn here is shifted to the right by 2. So the whole signal here is shifted to the right. It will start with n equal to 2 instead of n equal to 0 at the first example, at the original xn. So it will start at 2. So the value here is 1 to 1. Okay, follows the value of original. And if xn plus 2, it means that the signal here is shifted to the left by -2. Okay, so the signal here starts from -2, -1, and 0. And the values here, similar to xn here, is 1 to 1. So here is also 1 to 1. Okay, so we have a look at some of the exercises here. And we have x1n and x2n with different values. And then try to perform all of these signal operation in terms of discrete time signal. Okay, and we can discuss some of the examples after this. Example here, the exercise 2, yn is equal to n plus x2n. Okay, so what you have to do first is you perform the time reversal for x1n and become 0 and also -1, and the value here is 1 and also 1. x1 minus n, and then you add x2n. Okay, so you draw at -2, -1, 0, at 2, 1, 1. So basically when you want to perform the arithmetic operation for discrete signal, it's easier for you to redraw like this. Okay, it may take sometimes, but if the question here is quite complex here, then it's easier for you to draw. Okay, so that you won't make any mistake. So you just add based on the n here. From when n equal to -2, okay, there is no signal at x1n. Okay, here, so this is 1 plus 1, sorry, 1 plus 0. So at -2, only value 1. Okay, I think the easiest way is for you to put the n involved first. So the n involved here is -2, -1, and then 0. N equal to 0. So at -2, 1 plus 0 is 1. At n equal to -1, 1 plus 1, so it will become 2. And then at n equal to 0, it is 2 plus 1. So it will become 3. Okay, so this is an answer for first question, yn is equal to x minus n plus x2n. Question is, for the next question, change this one first. It involves shifting yn is equal to x1n, sorry, this is 1n plus x2n. So x1 here is the same. It has 0, 1 value it has 1 value at n equal to 0 and 1. And x2 is x2n minus 3 is this x2n signal, which is delayed to the right by 3 steps. So instead of starting at -2, it starts at 3 minus 2, which is, okay, this is plus, it starts at 1, 2, and 3. Okay, so the signal here is 1, 1, and okay, so again, x2n minus 3 is x2n signal here shifted to the right. Okay, because here it says n minus 3 means that it is shifted to the right by 3. So you shifted all the signals to the right. So instead of starting at n equal to -2, it starts at n equal to 1. So you just add together, okay, you will get the signals at 0, 1, 2, and 3. 0 at n equal to 0, 1 plus 0 is 1, at n equal to 1, 1 plus 1 is 2. Okay, so better you, if you want to sketch, it's better for you to put the values of the magnitude, okay, on top of your line here. And at n equal to 2, the value here is 1, and at n equal to 3, the value here is 2. This is the new yn. Okay, yn. Here, see yn equal to adds to negative n minus 2. So this is when it will be a bit tricky. So if you want to do in terms of plotting this, okay, what we can do here is we put the negative here outside the bracket, and then inside the bracket we put like this, n plus 2. If we look here, there is a time inversion and also time shifting involved. My question is, which one you want to perform first? Whether you want to shift first and then you want to do the time inversion. In which, if you choose anyone that you would like to do first, it will give you different answer. So which is wrong. So what we can do here, what you have to remember here is first you settle the inversion. Okay, settle the inversion first. Or you solve the inversion first, and then only you shift the signal. Okay, so when you perform the inversion for x2n, it will become something this. We start at 0, 1, and 2, and the value here is 2, 1, 1. Okay, this is x2, and then you shift by 2 to the left. Okay, because this is plus 2, so and d here is negative 2. So you shift by 2 to the left, so the new signal will start at negative 2, 1 and 0 will becomes 2, 1 and also 1. Okay, you can also do just like what we did before in time continuous, where you represent here the whole things in the bracket here as tau. Okay, so at your home you can try to do this. You represent the whole things, the whole numbers here in the bracket here as tau, and you do exactly like what you did in the continuous time, and you will get this answer. But if you want to make it simpler, okay, you can remember this rule in which you have to settle the inversion first and then shifting. And remember that when you want to solve for the inversion, you have to put all the means that you have to put something here, okay, whether it's negative or positive, okay, to represent the inversion, okay, outside of the bracket. Okay, outside of the bracket, you cannot do the inversion negative n, because otherwise, if you want to do the inversion negative n and then you shifted by negative 2, it will be wrong. Okay, you have to do like this. Right, so for the next lesson, I will show you about discrete system. Okay, so for the discrete time signals, you can try to do question D and E by yourself. Right, so